Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you like the content, if you find it useful, please consider liking, commenting, sharing, and most importantly, subscribing to our channel. We're very small at this point, but we'd like to grow. We'd like to reach more people. So any little interaction that you can do will help us out with that. In this current video, what I want to do is I want to continue the discussion on integration by partial fractions. So this is integration by partial fractions, part 3. What we're going to look at is when the integrand is a proper rational function and the denominator has an irreducible quadratic factor along with linear factors. I'll explain what irreducible quadratic means here in a second. For example, let's look at just the algebraic manipulation of adding the following two expressions together. This one has an x squared plus 1, so this is quadratic, and this one is linear. If I add those two together, of course I have to find common denominators, which would be their product. The first expression here, the first factor, or first fraction rather, the numerator would have to have a factor of x minus 2, and then this one would have to have a factor of x squared plus 1. That would give me this with that common denominator. Combine like terms, we come up with the following. A quadratic over, well, if I were to multiply this out, it would be a cubic. Notice I started with two proper rational functions. One has a quadratic denominator, one has a linear denominator. And again, when I add those, I still come up with a proper rational function, right? The numerator is a quadratic, and then the denominator is a cubic. Okay. With that in place, we'll refer back to that here in a second. Let's look at the following scenario. Suppose I had this expression, and again, we're thinking of, what if I had this expression as an integrand inside of an integral? This has, x squared plus 1, and then an x minus 3, so a quadratic, and then a linear. Now my question is, what if I were to, would it be possible to figure out what two expressions I would have added to obtain that? In other words, if I started with this, could I come up with these two? As we can see throughout these algebraic steps here, going in reverse, if I have this is what I would have started with. Now, this right here, if that was an integrand, is pretty challenging to integrate, right? However, these two terms are pretty simple. Just like in part 1 and part 2 for integration by partial fractions, I want to decompose a complicated proper rational function into simpler proper rational functions. All right, so then the question becomes, well, what could the numerators have been? If I look back through here, this one, just like in part 1 and part 2, would have just an arbitrary constant, right? Because it has to be a proper rational function. Therefore, I would have an arbitrary constant on top. What about this term? What could the numerator have been? In this previous example, I had 2x plus 1. In other words, it had to be a proper rational function. In order to be a proper rational function, the degree on top has to be less. And as long as it's 1 less, it's still proper, meaning that this would be, I'm going to change that letter here in a second. This would have to be something of the form ax plus b, and then let's change that to ac. They're arbitrary, but usually we go in alphabetical order starting from the left. Then the task is let's discover what A, B, and C would be. All right, let's go through that with this example. So find A, B, and C. Use the same terminology as we did in the previous two parts to this sequence of videos, where this we'll call our generic expansion. From the generic expansion, we come up with the coefficient equation. Remember, the coefficient equation comes from clearing the fractions. And to clear the fractions, they just multiply by this whole initial denominator, because, of course, this and this are factors of it. So I go ahead and I multiply through by that denominator here on the left, and we obtain the following, which again is what we call the coefficient equation. We get x minus 2 is equal to, well, in this case, the x squared plus 1 would cancel, leaving a factor of x minus 3. Therefore, I get ax plus b, and then x minus 3. Plus, with the term on the end. Of course, when I multiply this denominator by this, the x minus 3 would cancel, leaving x squared plus 1, and therefore I get c times x squared plus 1. Now what we did in part 1 and part 2, after I got my coefficient equation, is we were able to choose some convenient values of x. And convenient values of x allowed us to zero terms out and solve for the different constants. Well, I'm going to start that way here. Notice if I plug in x equal to 3, that's going to zero this out, and then I would have just one equation with a c. Let's start by doing that. Let's let x equal 3. Everywhere where I have an x, I'll plug in a 3. On the left, I have 3 minus 2, which is 1. On the right, this would be ax plus b times 3 minus 3, which is 0. That whole term would be 0, plus c times, if I plug in 3, 3 squared is 9. 9 plus 1 is 10, giving me 1 equals c times 10. Therefore, c is 1/10. Therefore, I have the numerator for this term on the end. Now, how do I find a and b? There's two different ways I can go about this, and I'm only going to do one of the two ways. What I'm going to do is I'll talk through the way that I'm not going to do, just to kind of give you an alternative. But let me do that first. Let me talk through the way that I'm not going to do it. I could plug in, let's pick two values that are other than 3, like x equals 0 and 1, right? If I plug in x equal to 0, I know the value of c, remember, that would give me one equation with a and b, plug in the other x value, that would give me another equation, a and b, and then I could solve that system of equations. I'm not going to do it that way, but you could check to see that that will work as well. Here's what I'm going to do. I'm going to leave the c as c. I'm going to leave it, I'm not going to put in 1/10 until the end. I'm going to multiply this out and turn it into a quadratic equation. And I'll show you why I'm going to do that here in a second. Let me go ahead and multiply this all out. X minus 2 would be ax squared. Ax and negative 3 minus 3ax. B and x would be plus bx. B and negative 3 minus 3b plus cx squared plus c. Let's combine like terms and turn this into a quadratic equation. 0 is equal to the x squared terms. I've got an a and then a plus c. A plus c x squared plus, well, how about the x terms? Well, I've got a b, a minus 3a, and I've got this x, but remember when I put on the other side, it would be a minus x. Therefore, I would have, let's say, b minus 3a minus 1x plus, and then what are the constant terms? I would have this negative 2, of course, becomes a positive 2 on this side. Then I've got a minus 3b and then a plus c. Therefore, you'd have, say, 2 minus 3b plus c, and then I'll just group that together to illustrate that that's the constant term. All right, I'll like that again, take my coefficient equation and distribute, combine like terms, rewrite it as a quadratic equation. Remember, a, b, and c are constants. Therefore, this would be a number times x squared plus a number times x plus just a constant equal to 0. So it's a quadratic equation in x. Okay, now let's go back to the discussion we had up here. Remember I said I can plug in x equal to 3. That satisfies the equation. I can plug in 1, 2, 0, negative 1, pi, 18,000, whatever I want to plug in. This is satisfied for every x value. Well, this and this are the same equation. I just rewrote the terms. But now here's the key. This is a quadratic equation with more than 2 solutions. In fact, it has infinitely many solutions. But more specifically, since it's a quadratic with more than 2 solutions, the only way that that can happen is if every single coefficient is 0. That's the only way that we can have a quadratic equation with more than 2 solutions, because remember that quadratic equations have where the leading coefficient is non-zero, can have at most, well, has exactly, I shouldn't say at most, I should say exactly 2 solutions. They could be real complex or repeated, but there's exactly 2 solutions. This has more than that, therefore, each of these coefficients is 0, giving me a plus c equals 0, b minus 3a minus 1 is 0, and 2 minus 3b plus c is equal to 0. So I have those 3 conditions. Now the fact that I already know what c is automatically gives me a. If c is 1/10, then this says that a would be negative 1/10. Now I know a, so I can solve for b. b would be 3a plus 1, which would be negative 3/10 plus 1. Of course, 1 is 10/10. That gives me b would be 7/10. Now I've got my a, b, and c value, and we can plug those into those expressions, and then we have our decomposition. Let's summarize that on the other side of the board. And in fact, let's do a little bit more than just summarize the result that we have. Let's pretend we were starting with the following example. Compute the integral of x minus 2 over x squared plus 1 x minus 3 dx. So if I was given this integral, what I would want to do, solution, I would want to take this expression and do the partial fraction expansion. That's exactly what we did in this previous example. And then once I do my partial fraction expansion, then I replace this integrand with this integrand with the constants filled in. That would give me the following. A, we found, was negative 1/10. So I have negative 1/10 x plus b, which was 7/10 over x squared plus 1. C was 1/10, giving me plus 1/10 over x minus 3 dx. All right, now our task is to integrate this. For this first term, what I'll do is let me separate the fraction, giving me the following. And I'm going to do 2 things. I'm going to separate the fraction. I'm also going to take these constants and pull them outside the integral. So I'm going to write this as 3 integrals. Negative 1/10 integral x over x squared plus 1 plus 7/10 integral 1 over x squared plus 1 plus 1/10. Of course, I ran out of room. Give myself some space here so that I can then compute the integrals. Might as well erase this whole thing. back to where I was, plus 1/10 integral 1 over x minus 3 dx. Complicated proper rational function, simple proper rational functions. Let's go through each one of these. Let's start over here. This is the easier one. I guess easy is relative, but you know what I mean. This one would turn into a natural log. This one, 1 over x squared plus 1. Think about that for a second. Where have you seen that expression? Right? Antiderivative is the inverse tangent. This one right here would be a u substitution. Notice that I've got a product, well, a division multiplied by the reciprocal. So you could think of it as division or product. I've got a product along with a composition. X squared plus 1 is plugged into the denominator, and this is a constant multiple of the derivative. Okay, so what I can do for each one of these, if I want to do a u substitution, u is x squared plus 1, du would be 2x dx, meaning I need a factor of 2, so then I'll cancel that by putting a factor of, cancel that by putting a factor of 1/2. Okay. For this one, I don't have to do any manipulations. It's just going to be an inverse tangent. This one, I don't have to do any manipulations. It'll just be log of x minus 3. Okay, so then I go ahead and then I integrate this. I'm going to get, first and foremost, this first integral, negative 1/20th integral of 1 over u du plus, I'm just going to say dot, 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 just so I don't have to rewrite that. And then we go to the next line. I'm going to get negative 1/20th. 1 over u would give me the natural log of the absolute value of u plus those other integrals. And then now we go to the last statement, which would give me the negative 1/20th natural log absolute value of x squared plus 1. Of course, x squared plus 1 for real numbers is always non-negative or always strictly positive. Absolute value bars are redundant, but it's a good idea to at least initially put those in there. And then plus 7/10. This one again was an inverse tangent. Last one, plus 1/10. Natural log absolute x minus 3. And then plus c. Okay. The majority of the work comes through algebra, okay, with any partial fraction expansion. All right, I'm not going to do any additional videos on partial fractions. So far, we kind of keep expanding on what the denominator was. We could say, okay, well, a cubic. Well, a cubic is going to reduce to a quadratic and then a linear. And then 4th degree, 5th degree, 6th degree, etc. It just gets a little bit too complicated, too redundant. And usually in your class, you'll end up with x squared, a quadratic times a linear, and you probably won't go any further than that. And that reminds me, I did mention earlier that I was going to mention or discuss what we meant by irreducible quadratic factors. All right, so just really quickly here, reducible versus irreducible quadratic factors. Let's look at x squared minus 1 versus x squared plus 1. This is the difference of squares. This is a sum of squares. Well, the difference of squares, of course, factors as the sum of the bases and then the difference of the bases, which means that I can reduce this quadratic to a product of linear terms. Now, if you know about complex numbers, you know that I can also reduce this to a product of linear terms. However, in your introductory calculus sequence, complex numbers play no part. Therefore, this is reducible, this is irreducible. More precisely, this is reducible over the real numbers. This is irreducible over the real numbers. This one actually is reducible, but over the quadratic numbers. Over the complex numbers. This is reducible over complex numbers, but it is not reducible over real numbers, because since it's complex, it's not in the real number system, and therefore this does not factor using real numbers. So when I say irreducible quadratic, we'd have like x squared plus 1, or x squared plus 4, x squared plus 9, something along those lines. Okay. All right. Thank you for watching, and don't forget to subscribe, like, comment, and share.